Hello everyone, I welcome you all to the course UAV design, and in today's lecture we're going to see about fuselage design steps and fuselage configurations of different unmanned aerial vehicles. The primary function of a UAV fuselage is the accommodation of the payload and the autopilot, as it serves as a central structural unit that protects internal subsystems. The design process is multidisciplinary, as the fuselage configuration impacts aerodynamic performance, stability, and protection cost. These three are interconnected in this, and that's the reason why we call it as multidisciplinary. The design of a UAV fuselage follows an iterative systems engineering approach, moving from requirements to a finalized mathematical loft. The recommended steps are summarized as follows. The very first one is requirement identification. During this phase, the list of design requirements, including mission profiles, airworthiness, and crashworthiness standards, are listed. The second one is payload and system selection. During this phase, we identify all sort of payloads, for example, cameras, radars, sensors, and communication elements, noting their geometries and the power needs. And also, volume is considered in this case of the payload to ensure that it is properly housed inside the fuselage. The third one is component sizing. Here we identify the largest internal component to establish the required maximum diameter of the fuselage. The autopilot and pressurization. Since the autopilot compartment and determine if the pressurized compartments are needed for heat generating avionics at high altitudes. There are many sensors and gadgets which are installed in an unmanned air vehicles which require cabin pressurization system and air conditioning system to maintain the temperature, because it will be continuously working and it will generate some temperature. So temperature keeps on increasing. So in order to control the temperature, we maintain air conditioning system inside the fuselage. The configuration and internal layout. Select the configuration and arrange internal sections such as nose, rear, fuel, wing box symmetrically about the exit plane. The geometric optimization. Establish the optimum length to diameter, that is fineness ratio. For most low speed unmanned aerial vehicles, a ratio between 5 and 10 is recommended. The structural integration. Allocate space for the wing to carry through box near the CG to handle large bending moments. Nose and rear design. Design the nose for sensor visibility and the rear section with a taper or upsweep angle that avoids the tail strikes during the takeoff. Basically, when it is designed such that to ensure that there is some clearance, else this will be striking or colliding with the surface, this part. Lofting. It is the mathematical tool which we apply for the modeling to define the external skin geometry, ensuring smooth aerodynamic contours to minimize drag. We'll be having, for example, if we take the wing, we'll have the different ribs, and these ribs will be joined with a longeron and a skin is laid over this. So what will be the angle of the skin that we measure and we calculate and measure using lofting techniques, which we have seen in the previous lecture. Last one is the analysis and feedback. The entire design is evaluated against performance, stability and weight requirements, and then returning to the earlier steps to refine the layout if deficiencies are found. UAV fuselage configurations are diverse, and often it utilizes different shapes that are not constrained by the need for an onboard pilot. The very first category in this is horizontal takeoff and landing configurations, which is tail loft configuration. The most common arrangement where the center of mass is forward of the wing center of lift, balanced by a down load on the tail. High altitude, long endurance unmanned aerial vehicle and medium altitude, long endurance unmanned aerial vehicles typically use this configuration of fuselage for long fuselage that carry significant equipment and fuel. The second category is canard, tail forward. The foreplane generates positive lift, making it aerodynamically more efficient through directional stability, which is harder to achieve without swept wings. Tailless or flying wing configuration. These minimize radar signature and wetted area, making them ideal for stealth combat UAVs. Twin boom arrangement. Extremely popular for pusher propeller unmanned aerial vehicles because it leaves the nose clear for surveillance payloads while protecting the engine. Blended wing body configuration. The wing is smoothly blended into the fuselage, reducing wetted area and drag while allowing the entire vehicle to generate lift. Whale shaped high altitude long endurance fuselage, which is designed with a bulbous nose to house a large satellite communication antenna. If best example is Global Hawk unmanned aerial vehicle, which is having a similar kind of nose where the communication antenna is been loaded. Multi-fuselage is a specialized configuration which is used for heavy, high clearance payloads or for structural efficiency through span loading. Asymmetric configuration. Some concepts offset volume longitudinally in two smaller fuselages to seek supersonic drag reductions. Modular construction. In this configuration, small and medium unmanned aerial vehicles often use interchangeable modules like body, mechanical, electronics, and payload to facilitate maintenance and rapid roll-off changes. Internal arrangement fundamentals. Regardless of the configuration, the internal layout must prioritize stability and payload performance. Heavy usable loads like fuel tanks must be placed near the aircraft CG so that the CG does not shift significantly as fuel is consumed. Furthermore, radar dishes must be positioned with a clear line of sight to satellites or targets, often requiring specific radome design in the nose or upper fuselage. Concluding this lecture, the unmanned aerial vehicle fuselage is far more than a simple structural shell. It is a central integrating element that directly influences aerodynamic efficiency, stability, payload effectiveness, manufacturability, and overall mission success. Its design demands a systematic iterative approach that begins with clear mission requirements and progresses through component sizing, configuration selection, structural integration, and geometric refinement. Because the fuselage governs internal layout, CG management, and external aerodynamic form, each design decisions must be balanced performance, weight cost, and operational constraints. The wide range of unmanned aerial vehicle fuselage configurations, from conventional tail aft layouts to blended wing bodies and twin boom arrangements, demonstrates the flexibility enabled by the absence of an onboard pilot. Each configuration offers distinct advantages depending upon mission objectives such as endurance, stealth, payload capacity, or surveillance capability. Ultimately, an effective fuselage design harmonizes internal subsystem accommodation with external aerodynamic optimization, ensuring that payload, functionality, structural integrity, and flight performance are achieved in a coherent and efficient system. These are the references used for this lecture. Thank you.